Welcome to Lesson 10. This lesson is titled Connecting Equations to Graphs. In today's lesson, we're going to investigate what graphs can tell us about the equations and relationships they represent. We have three learning targets today. Number one, I can describe the connections between an equation of the form ax plus by equals c, the features of its graph, and the rate of change in the situation. Number two, I can graph a linear equation of the form ax plus by equals c. And number three, I understand that rewriting the equation for a line in different forms can make it easier to find certain kinds of information about the relationship and about the graph. So at the end of the lesson, if you're comfortable with all three of these, then consider this lesson a success. If you still have questions, then please bring those questions to class so that I can clarify those answers for you. Our warm-up today is 10.1, titled Games and Rides. It says Jada has $20 to spend on games and rides at a carnival. Games cost $1 each, and rides are $2 each. Number one, which equation represents the relationship between the number of games, which is x, and the number of rides, which is y, that Jada could do if she spends all her money? So as we look through here, we can see that games are x, and games cost $1 each. So we want to make sure that x is 1x. So that could be A, and that could be C. Then we see that number of rides is y, and rides are $2 each. So we want to make sure we have 2y. So we want to make sure that we have 2y. We don't have that in A, but we do in C. Then we want to make sure that there's a $20 total. And that is what we have in C. So C would be our correct answer. So next they want us to explain what each of the other two equations could mean in this situation. So if we look at A, we have 1x. So that is going to mean that games cost $1 each because x is number of games. So for A, we have $1 games, but we also have y, so that would mean we have $1 rides. And then we have $20 total, so that's still correct. In B, we have 2x, so that would mean we have $2 games. And that we have y, so we have $1 rides. But what we wanted was C, where we had $1 games and $2 rides. So we have to make sure we understand how to take the information that's in the equation and put it in equation form. So our first activity today is 10.2, titled Graphing Games and Rides. It says here are the three equations. Each represents the relationship between the number of games, which is x, the number of rides, which is y, and the dollar amount a student is spending on games and rides at a different amusement park. And then they give us three separate equations here. And it says you can choose 1 to 2 equations For each assigned or chosen equation, answer the questions. So here it says we need to fill in our first equation. So the first equation they give us is x plus y equals 20. So we can go ahead and write that in here. X plus y equals 20. Number one, what's the number of rides the student could get on if they don't play any games? On the coordinate plane, mark the point that represents this situation and label the point with its coordinates. So, if they don't play any games, and we look back and we see that games is x, then we would have 0 plus y equals 20, which means that y equals 20. So if we have 0 games, we have 20 rides, and we can put a point right here on the graph. Number 2, what's the number of games the student could play if they don't get on any rides? So now we want rides to be y and rides to be 0, and rides is y. So now we have x plus 0 equals 20, which means x equals 20. So if we don't get on any rides, we can get on 20, or we can play 20 games. So now we have our two coordinates. Now they want us to draw a line to connect the 2 points that we have drawn. So now if I go in here, drawing a line to connect them, looks something like this. Complete the sentences. If the student played no games, they can get on blank rides. Well, here we said that no games allows them to be on 20 rides. For every additional game that the student plays X, the possible number of rides Y, and they want us to choose increases or decreases. So if we look, we see that our line goes down. So as we increase the number of games, we see that our number of rides is decreasing. So we can put decreases in this blank. Then it wants to know how much it decreases by. So if we look, as I increased games by 2, I decreased rides by 2. So that means every time I increase games by 1, I am decreasing rides by 1. So we can put 1 right here. They want to know, what is the slope of our graph? Where does the graph intersect the vertical axis? So first off, slope is how much we change in the y direction over how much we change in the x direction. So if we say slope, that is change in the y direction over change in the x direction. You also may have heard of rise over run. So when we looked at our graph, we were going down by 1 every time we went to the right by 1. So -1 over 1 is -1. So our slope is -1. They want to know, where does the graph intersect the vertical axis? So if we look, this is our vertical axis, and we had our point on 20. So vertical intercept equals 20. Now they want us to rearrange the equation to solve for y. So if we remember, our original equation was x plus y equals 20. To solve for y means I want y by itself. I need to get rid of the x on the left, and if this is positive x, then the opposite is minus x, because now x minus x equals 0, and it goes away. But if I subtract x from the left side, I also need to subtract x from the right side so that my equation stays equal. So now I have y equals 20 minus x. What connections, if any, do you notice between your new equation and the graph? So if we think about our new equation, we said that our vertical intercept was 20. And we see that right here. And we said that our slope equaled -1, and we can see that right here attached to our x. So we can see that the number that is not attached to x ends up being our vertical intercept, or our y-intercept. And we can see that the number that's attached to the x becomes our slope. So now they want us to do the same thing with a second equation. So if we go back, we can do this second equation here. 2.50x plus y equals 15. So 2.50x plus y equals 15. Number one, what's the number of rides the student could get on if they don't play any games? So if we remember, games is x. So if we're not playing any games, we have 2.50 times 0 plus y equals 15. Anything times 0 is 0. And now I just end up with y equals 15. So when there's no games, I can go up to 15 on the y-axis and put my point right here. Number two, what's the number of games the student could play if they don't get on any rides? Well, rides is y. So we're going to substitute 0 for y. Now we have 2.50 2.50x equals 15. 2.50x is multiplication. Opposite of that is division. Now anything divided by itself is just 1, so that goes away. And if I divide the left side by 2.50, I must divide the right side by 2.50 so that my equation stays equal. This results in x equals 6. So now, if there are no rides, there are 6 games. So I can put my dot right down here. Number 3, draw a line to connect the 2 points you have drawn. So I can start here and just draw a line connecting these 2. Complete the sentences. If the student played no games, they can get on blank rides. Well, we said 0 games resulted in 15 rides. For every additional game the student plays X, the possible number of rides Y, we see that our line goes down from left to right, so this is decreasing. By some number. So if we look at our line, we start at 15 and go to 0. So that is negative 15 change in y. For our x, we start at 0 and we go to 6. Both of these numbers are divisible by 3. So if I divide 15 by 3, or negative 15 by 3, I get negative 5. And if I divide 6 by 3, I get 2. So this tells us how much we're decreasing each time. We are decreasing by 5 halves every time we increase the number of games by 1. So now they want to know, what is the slope of our graph? Well, we just found our slope. Our slope equals change in y over change in x. We said our change in y was negative 15, and our change in x was positive 6. We divided negative 15 by 3, and we got negative 5. We divided 6 by 3, and we got 2. So our slope is negative 5 halves. Where does the graph intersect the vertical axis? We said that our y-intercept was at 15. Now they want us to rearrange the equation to solve for y. Solving for y means we want an equation that says y equals. So we had 2.50x plus y equals 15. So we are going to subtract 2.50x from the left side so that it goes to 0. But if I subtract it from the left side, I must also subtract it from the right side. Now I have y equals 15 minus 2.50x. What connections, if any, do you notice between your new equation and the graph? So first off, we said Our equation is y equals 15 minus 2.50x. We said that our y-intercept was 15. And again, we see that the number that is not attached to the x ends up being our y-intercept. Then we said that our slope was change in y over change in x, which was negative 15 over 6. We divided negative 15 by 3 and got negative 5. We divided 6 by 3 and got 2. Negative 5 halves is negative 2.50. And we can see that our slope, again, ends up being the number that is attached to our x-axis. How did we find the number of possible rides when the student plays no games? We substituted 0 in for x because x was the number of games, and then we solved for y. How did we find the number of possible games when the student gets on no rides? Well, rides was represented by y, so we substituted 0 in for y, and we solved for x. Where on the graph do we see those two situations? All games and no rides. Well, we see that at the x-intercept because games was x. Or all rides and no games. We saw that at the y-intercept because rides was represented by y. The three equations are all given in the same form. ax plus by equals c. What information can you get from an equation in this form? What do the a, b, and c represent in each equation? So if we think about the original equations, there is a pattern that you might have noticed. In every situation, we can actually find our slope and our y-intercept using the coefficients in the a, b, and c position. If we want our slope, then we can take a, which is the coefficient in front of x, and we can divide it by b, which is our coefficient in front of y, and that will give us our slope. So in the first equation, if you noticed, we had 1 as our a and 1 as our b. And we need to take negative a. So this would give us negative 1 divided by 1, which equals negative 1. And we said that was our slope. If we think about our second equation, negative a would have been negative 2.50, and our b would have been 1, and we ended up with negative 2.50, which was our slope. Then, when we think about our y-intercept, because rearranging this, we would need to divide anything on the right by b. Our y-intercept would end up being c, divided by B. So if we think about our original one, we had a C of 20 and a B of 1, which gave us our y-intercept of 20. When we think about our second equation, our C was 15 and our B was 1, and that gives us our y-intercept of 15. So as you are looking at ax plus by equals c, you'll be able to see that your slope equals negative a, because rearranging it, you would subtract ax from both sides, and then you would end up dividing by b to move it to the right side. So your slope ends up being negative a divided by b, and your y-intercept ends up being c divided by b. If we rearrange the first equation and solve for y, we get the equation y equals 20 minus x. Is the graph of this equation different from that of the original equation? No. When you rearrange an equation, you write an equivalent equation. And if they are equivalent equations, they will have the same solutions. Therefore, their graphs will also be the same. You were asked to complete some sentences about what would happen if the student played more games. How did the graph help you complete the sentences? Looking at the graph, we can see that we always had a negative slope. As the games increased, the number of games decreased. We were able to notice this on the graph. Would you have been able to see the trade-offs between games and rides by looking at the original equations in standard form? Yes, because we know that the slope is going to be negative a divided by b, we can tell whether this is going to be a negative slope or a positive slope, and then tell how games and rides relate to each other. Do the rearranged equations still describe the same relationships between games and rides? Again, yes, all we are doing is rearranging the equations. The equations are still equivalent to each other and therefore still have the same solutions. It has not changed the relationships at all. What new insights does this form of equation give us? The standard form of the equation allows us to find the slope and the y-intercept by understanding that negative a divided by b is our slope and c divided by b is our y-intercept. Our next activity is 10.3, nickels and dimes. Andre's coin jar contains 85 cents. There are no quarters or pennies in the jar, so the jar has all nickels, all dimes, or some of each. Write an equation that relates the number of nickels n, the number of dimes d, and the amount of money in cents in the jar. So, first we have to know that a nickel equals 5 cents. Therefore, every time we have a nickel, it needs to be multiplied by 5 cents. And we know that dimes are 10 cents. So every time there's a dime, it needs to be multiplied by 10 cents. And we know that there's 85 cents total in the jar. We need to add the number of cents made from nickels to the number of cents made from dimes, and that will equal the total 85 cents that are in the jar. Now they want us to graph our equation on the coordinate plane and include axis labels. So we could say that nickels are on the bottom, so that's number of nickels, And we could say that on the y-axis, we have number of dimes. So we know that if we put 0 in for nickels, then we have 0 plus 10 times dimes equals 85. To get rid of the 10, I would need to divide by 10 on the left and divide by 10 on the right. This leaves us with dimes equals 8.5. So if there are no nickels, there are 8.5 dimes. Then we can do the opposite. We can say if there's no dimes, then we have 5n plus 0 equals 85. I'm going to divide by 5 on the left, so I need to divide by 5 on the right, and n equals 17. So if there are no dimes, there would be 17 nickels. Then we can draw the line connecting these two. How many nickels are in the jar if there are no dimes? So at no dimes, we come down here to the x-axis, and we say there are 17 nickels. How many dimes are in the jar if there are no nickels? We go over here to the y-axis where we have no nickels, and we go up to our y-intercept, which was 8.5 dimes. Could each of these graphs be used to represent the relationship between the quantities? Notice on the top two, we have dimes on the y-axis and nickels on the x-axis. But on the bottom two, they have changed those so that nickels is our y-axis and dimes is our x-axis. So these two are the same, just with the labels flipped. So now we need to think. If I have a solid line, I am saying every single point on that line represents a real solution. But I need to go back to when we thought about constraints. Can I have partial dimes and partial nickels? And the answer is no. So I could not have solid lines for my graph, because this would mean I have 8.5 dimes, or I have some other partial dimes or nickel combinations along the way. We need to have only whole number nickels and only whole number dimes. So the top right graph could be correct, and the bottom right graph could be correct, but not the two on the left. Suppose we were to express the relationship between the same quantities, but in dollars instead of cents. What would the equation look like? So originally, we expressed it in cents, and nickels was 5 cents. So we wrote the whole number 5. But now if we're going to write it in dollars, we don't want to say 5 because that would represent $5. We would need to say 0.05 N. Now this is 5 cents if whole numbers are dollars. The same kind of change needs to happen with dimes. If we are in dollars, then dimes are not 10D, they are 0.10D to represent 10 cents. And our final total is not 85 anymore because now we're representing dollars instead of cents. So now it needs to be 0.85. So we need to pay attention to what these amounts are being represented in. If it's in cents, that is going to be written differently than if we say we are representing dollars. What would the graph of this equation look like? Try graphing it on the same coordinate plane. Well, if we think about it, if we said we had no nickels, then we would just have 0.10 dimes equals 0.85. We would divide the left by 0.10. We would divide the right by 0.10. And this would still result in dimes being 8.5. So the y-intercept doesn't change at all. Now let's try it the other way. If we say we don't have any dimes, 0.05 nickels equals 0.85. I would divide the left by 0.05. I would divide the right by 0.05. And I would still end up with nickels equals 17. So when I graph these, I would graph it the exact same way because I now represented both sides of the equation in cents or in dollars instead of cents. So I did the exact same change to the left that I did to the right, so therefore nothing changes. And that is why the graph would be identical. In our lesson synthesis, we saw equations in different forms representing the same constraint. For example, x plus 4y equals 28 and y equals 1/4. X plus 7. Both represent the games and rides the student could do with a fixed budget. What information about the situation and about the graph can we gain from the standard form ax plus by equals c? Again, what we have seen is that our slope equals negative a divided by b. So if we look here, my a is 1. So that's negative 1. My b is 4. So I have a slope of negative 1/4. So on this one, we can see that when we rewrite it, the number with our x is going to be our slope. And our y-intercept is going to equal c divided by b. Well, our c was 28, and our b was 4, and 28 divided by 4 is 7, which is going to be the number that is not attached to our variable. So ax plus by equals c will tell us our slope if we remember that slope is negative a divided by b. And it will tell us our y-intercept if we remember that c divided by b is our intercept. What information does the slope-intercept form give us? Well, the slope-intercept form is our form that is y equals mx plus b. And in slope-intercept form, m is our slope and b is our y-intercept. What might be an efficient way to graph an equation of the form ax plus by equals c? The easiest way is to graph your intercepts. Let x be 0 and solve for y. Then let y be 0 and solve for x. You can graph your y-intercept and your x-intercept and then draw the line that connects them. Our cooldown today is on Kid'em. It is 10.4 Kieran at the carnival. Kieran is spending $12 on games and rides at another carnival, where a game costs 25 cents and a ride costs $1. Number one, write an equation to represent the relationship between the dollar amount Kieran is spending and the number of games X and the number of rides Y that he could do. So if we take this statement by statement, he is spending $12. That is going to be our total. Games cost 25 cents each and are represented by X. So that's 0.25X. Rides cost $1 each and are represented by Y. So if we add the total cost of games to the total cost of rides, we would get the total money of $12. So that would be how we would write the equation. Then they want to know which graph represents the relationship between the quantities in this situation and explain how we know. Well, if we think about our equation, we said that 0.25x plus y equals 12. Our slope is negative a divided by b. So in this case, that's negative 0.25 divided by 1, which is negative 1/4. Our y-intercept is c divided by b. In this case, that's 12 divided by 1, which is 12. We can see that this has a y-intercept of 12, this has a y-intercept of 12, and this has a y-intercept of 12. So now we can look at the slope. We have a slope of negative 1/4. Well, this slope is going up from left to right, so that cannot be the answer. Now if we look at B, this one is going down, and C is also going down. But this goes from 12 to 0, a change of negative 12, as X goes from 0 to 3. That is a slope of negative 4, and we have a slope of negative 1/4. So it can't be B. Now if we look at C, we go from 12 down to 8, which is a change of negative 4, as X changes from 0 to 16. Negative 4 can be divided by 4 once, and 16 can be divided by 4 times. Now I find my slope of negative 1/4, so this is the correct graph. Our only glossary term in this lesson is equivalent equations. These are equations that have the exact same solutions. So if you still have any questions, please bring those to class and ask me so that I can clarify them for you. Otherwise, thank you for taking the time to watch this, and I look forward to our next lesson.